Hi, class. In this recording, we're going to focus on some integrated functions of the brain, particularly sensation in this recording. So let's dive into it. As we're looking at our brain, it's important to note that higher brain functions, such as sleep, memory, cognition, emotion, these are going to be integrated all over the place. In particular, sensation, which is the key focus on what this recording is going to be on, motor control and language. These functions are going to be located primarily within the cerebrum. The cerebral cortex and the basal nuclei, brainstem, cerebellum, all these different parts of the brain need to interact with each other for these to work. And I can't emphasize this enough. There is no discrete anatomical boundary for most of the higher functions of the brain. They're kind of blended throughout. Our integrative or higher functions of the brain focus mostly on the cerebrum. It does involve different parts of the brain that we've already talked about previously in other recordings: the brainstem, the cerebellum, the diencephalon. So let's talk about sensation. We have our primary sensory cortex, sometimes referred to as the primary somatosensory cortex. This cortex is where sensory input is first going to be received by the cerebrum. And this is where we become conscious of a stimulus. So as we're looking at this primary somatosensory cortex, the fact that we have a primary one implies that we're also going to have some secondary or association areas. These secondary or association areas help the primary area to process sensory information, to interpret sensory information. You can think of it as kind of like a GPU that's a backup to the CPU within your computer, or a graphics processing unit as a backup to a central processing unit. The primary visual cortex is going to be associated with the visual association areas, and they allow us to make sense of visual stimuli. We also have, and notably, this primary visual cortex is within the occipital lobe. We also have multimodal association areas. And when we say multimodal, this just means that they do more than one thing. They're twofers or threefers. They can receive input from multiple senses and integrate them into an overall perception of what our surroundings are going to be. For instance, proprioception, our orientation in space, is a good example of this. We have multiple sensory receptors used to help us keep our body oriented in space. So let's talk special senses. These special senses are typically going to be sight, sound, smell, taste. They're going to be limited to the head and have some pretty complex organs. For example, eyeballs tend to be rather complicated. So as we look at vision, vision is going to be processed at the primary visual cortex. Let's shift to yellow here to be consistent. So we have our primary visual cortex right over there in yellow. And then right next to it in green, we have our visual association area. Right next to that within green, these areas help us to process what we're looking at. Now, it's also worth emphasizing that inferior regions of the temporal lobes deal with recognizing faces and familiar objects. So vision isn't just necessarily limited to the occipital lobe. Most of the processing does happen in the occipital lobe, though. As we look at hearing, our primary auditory cortex is going to be within the temporal lobe and the insula. The temporal lobe is right over here, and we have the primary auditory cortex located right there, that small little band that I just covered in green. Let me clear the screen there. So there's a darker pink right there. That's our primary auditory cortex. We also have an auditory association area. This is going to also be within the temporal lobe, and it's going to be deep and inferior to the primary auditory cortex. Let's shift to blue here. So this lighter pink area that I'm outlining in blue, that's going to be our our auditory association cortex, where we can recognize spoken words, familiar pieces of music, whose voice we're listening to on the phone, etc., etc. Well, we're looking at keeping our sense of balance or our sense of equilibrium. We're going to have a lot of that processed within the cerebellum. So we have our sense of balance, our sense of motion. We have the cerebellum down here, shown in brown, circling it in blue, helping us to keep our equilibrium. There are also several nuclei within the brain stem that are going to be associated with keeping our head and eyes moving appropriately. The association cortex for equilibrium is going to be located on the roof of the lateral sulcus. The lateral sulcus is this big indentation right here. So the roof of the lateral sulcus is going to be the superior margin of that. And this seat of consciousness of our body's movements and orientation in space. So this is a way for us to be able to know how we're moving around, to perceive the movement of our body throughout space. In terms of taste and taste and smell, our gustatory response or taste, sense of taste, is going to be processed by the gustatory cortex. We find the gustatory cortex at the inferior end of the postcentral gyrus. So here is the postcentral gyrus, and all the way down at the inferior end of that postcentral gyrus, not shown in this figure, would be the yes, shown in this figure in orange. I was right on top of it. It's the primary gustatory cortex. Sorry about that, guys. We also have our olfactory, or our sense of smell. And this sense of smell is going to be processed by the primary olfactory cortex. So we have our primary olfactory cortex at the medial surface of the temporal lobe. This temporal lobe, for those of you who don't remember, is associated with the temporal bone. And that primary olfactory cortex is going to be at that medial end. So let's talk general senses. In terms of general senses, when we talk about a general sense, we're going to refer to something that is not a special sense. So special senses are sight, sound, taste, and smell. And when we think of general senses, think of touch, temperature, pain. These things, I jokingly say, if an earthworm can process this, then it's not special. And these are all things that an earthworm can process. So as we look at these general senses, they are going to be all over the body and have relatively simple receptors. So another key thing that we need to emphasize here is that the receptors for general senses are simple. Now, as we're looking at the head, the cranial nerves that leave our head, cranial nerves are going to carry general sensory information. And to the rest of the body, instead of having cranial nerves, we're going to have a bunch of spinal nerves primarily carrying lots of this information. And the spinal nerves will enter the spinal cord, and then we'll have ascending tracts within the spinal cord. Now, as we're looking at the thalamus, our thalamus is that relay station, the biggest part of the diencephalon. It's going to process information from the contralateral side of our body. So when we have that information switching over from left to right. And it's going to be able to, the thalamus will be able to selectively relay information to the post-central gyrus of the parietal lobe. That post-central gyrus is where we have the primary somatosensory cortex. This cerebral fold is immediately caudal, or immediately posterior, as most people would say, to the central sulcus, and it's going to give us our awareness of stimulus. Now, as we're looking at the somatosensation, somatic association area, this area is even more posterior. It is caudal or posterior to the post-central gyrus, and it's going to allow for us to make cognitive sense of a stimulus. So it's the backup processing. So we have the primary somatosensory receptor, and then we have the association area. So to show on a figure, we have our central sulcus here. I'm going to outline that in red. There's our central sulcus. The precentral gyrus is rostral or anterior. post-central gyrus is caudal or posterior, and it's that post-central gyrus where we are going to have the primary somatosensory cortex, or where we are going to process sensation. And it's worth emphasizing that we don't have even distribution of processing. Our face overwhelmingly gets a lot of processing power dedicated to it. Our hands are also disproportionately large in terms of the amount of processing power that they get. And then our feet and genitals also get a lot of processing power dedicated to them. Other parts of our body which are not as sensitive include the arms, legs, and torso. These areas don't have as much processing power in terms of, or dedicated to them in terms of processing sensory information that's coming in. Now, as we're looking at that previous slide, that was a homunculus. It shows the distribution of the sensory processing over the cortex. And a lot of times it looks like an upside down map. So if I can back up a slide here. Previous. What we see here is that homunculus, where we have the parts of the body displayed over the gyri of the brain, showing where different parts of the body have their processing occurring. So what does this show us? This means, generally speaking, that it's just a good way for us to know what part of the primary somatosensory cortex is going to be responsible for processing information from a certain part of the body. So we have lower limbs that are going to go to the superior and medial parts of the gyrus. The face is going to be on the primarily lateral and inferior margins of the gyrus. And as we look at this process, there's a phenomenon known as somatotopy. Somatotopy. Yes, I did say it correctly there. That's kind of a tongue twister for me. So as we're looking at somatotopy, somatotopy is going to be the correspondence between an area in the body and an area in the central nervous system. This is a nice way of saying that we can make a homunculus. That's all we have for this recording. If you have any questions, please feel free to post them in the class discussion board or send me an email. And as always, happy studies.